Okay, if everyone can hear me, I guess we're gonna get started. So, welcome to the FRC Electrical Edition, um, I guess, presentation. So let's get started. So for goals, we're gonna just go over basic electrical concepts that don't necessarily apply just to FRC, such as digital versus analog, voltage versus amperage, current, PWM wire versus CAN wire. And we're going to review specific electrical subsystems, and we're going to explain the functionality of each of them. And if you have any questions, please do ask at the end of the presentation.
All right, so I guess I'm going to get started here. So this is, like Devesh said, this is a concept that is not exclusive to FRC. You're going to run across this like in everyday life and in any kind of electrical engineering you ever do. This is digital versus analog. This is actually pretty simple, but the difference is really important and they're not interchangeable. So a digital signal is like anything that you just turn on and off. So like a light switch is like the best example where it's like it's on, it's off. There's no middle ground. There's no halfway. You'll see that all the time in like FRC. So like limit switches on the robot will have, that is either open or closed once it's been pushed. And like any button on a controller is also the same thing. It's a digital signal. This is going to come up again, so hang on to that. For what it's worth, digital signals are described often low are basically the same thing, and on and high are basically the same thing. So that waveform there is demonstrating that bottom line, the off low line, that would be allowing like 0 volts through, and the on or the high line, that would be allowing whatever the source voltage is. So for FRC, that might be 12 volts or 5 volts, depending on what we're doing. Analog signals are just the opposite of that, where they can be anything between their minimum and maximum voltage or current, depending on the sensor. And this is like everything in your life that's adjustable is an analog signal. So like any light switch dimmer with that little wheel that you turn, that would be an analog signal. Joysticks, because they have like more positions than 0 and 1, they can be anywhere in between, that would be analog. Or like a distance sensor, something else we'd use in like autonomous. If a distance sensor were digital, it would basically tell you if there is or is not a thing there. Whereas if it's analog, it can tell you how close that thing is to you. All right, this is another general concept. I find this to be the best metaphor for voltage, current, and resistance. This is what I was taught in high school. I don't know if they're still doing that. But yeah, the idea here is that voltage is, in our case, pretty much static and basically represents like the amount of energy that is available. And current is the amount of energy that's coming through at any given time, or that you allow to come through at any given time, might be a better way to put that. And then resistance is what impedes that energy from coming through. So if you guys have heard of like a short circuit, that's basically anytime you have no resistance and there's nothing stopping the electricity from going as fast as it possibly can. So a short circuit has extremely high current because it has extremely low resistance. And the opposite is also true. So if you have very high resistance, very little current can get through. For most of FRC, we're dealing with pretty static numbers here, and a lot of that stuff is limited by the rules of the game anyways. But this is just a good thing to keep in mind. The main thing I want you guys to take away from this is that current and resistance are inversely related, and that voltage is sort of static, more or less. All right, and yeah, so this is just following up a little bit. You guys may or may not have heard about AC, which is alternating current, and DC, direct current. Those are both forms of electricity. AC is like the 120 volts that you get from your wall. There's a lot of complicated power station reasons that Bob could explain to you why we use AC in our homes instead of DC. But for FRC purposes, everything we deal with on the robot is in DC. and like 90-95% of it is 12 volts. That's the voltage that we get from our battery. That's the voltage that goes to the motors. That's the voltage that drives all the brains. There are also 3.3 volts, 5 volts, and 24 volts at different places on the robot for different devices. So like cameras and lower energy things. These are not interchangeable for the most part, as Tejas can tell you with his many experiences with the Raspberry Pis. Um, yeah, so I would say in general, if you don't know, ask, because this can go bad if you give something the wrong voltage. But the 3.3, the 5, and the 24 are pretty hard to find, and we'll talk about where you can get those later and when you might need them.
Okay, so moving on to the basic electrical system, we're going to be covering a bunch of these, I guess, parts of the electrical system, and we're going to just go through each one of them and just tell you a little bit about them and what they do and stuff. So, starting off with the battery, we use a 12-volt battery for our robots, and they're rated for about approximately 18 amp hours. They can put out 18 amps of current for 1 hour. That's hence the term. Or 36 amps for a half hour, or 72 amps for 15 minutes. So the way that FRC just works generally, we use a lot more than 18 amps. So we have to actually constantly interchange the batteries every match. And that's why we go through a lot of batteries if you watch, just generally when we're practicing and while we're in a match. A little bit about the battery. Of course, it's the main power source. You can't run a robot without a battery. Each battery has two terminals, one being a positive. In this case, it's the red one, while one is a negative terminal, which in this case is the black one. So moving on, connecting to the battery is the main breaker or the power switch. And as you can see here, the power switch is this black thing with a small red peg on it. And when this peg is pressed, a small arm or lever kind of comes out, effectively breaking the circuit off. So the switch has a limit of 120 amps for the entire robot, just in case nothing gets fried or too much power goes through the wires. Okay, moving on. So connecting from the switch is the power distribution board, or the PDB. And this is basically the great power diverter. It basically takes all the 12 volts coming in from the battery and distributes it accordingly to its red and black terminals. Each terminal pair are called channels, and each channel has to have a certain circuit breaker on it, depending on how much power is going through each of them. And you can actually see below, we have an example of a 40 amp breaker. So moving on to breakers, circuit breakers basically limit the amount of current that goes through a channel. And for example, like showed in the picture on the right, this is a 40 amp breaker, and it will not allow more than 40 amps to go through in a channel at a specific time. And you use different breakers based on whatever you are using. For example, if you're using a motor, you would use a higher breaker than you would, for example, some other part of the robot. And it also does make a clicking noise if the current limit is exceeded. So that's also nice. Moving on to the Rio. This is the brain of the robot. This is basically the thing where everything that needs to be programmed, everything that needs to be controlled is plugged into. And actually the Pi, Jason was mentioning, the Raspberry Pi is actually plugged in to this small slit that under the NI Robo Rio, and you can program directly into the Rio itself. So there are two separate. Yeah. So there are two separate ports. There's DIOs and there's PWMs, and each of them you use for a specific thing. Also, on the far left corner is a CAN terminal where you can put CAN in and daisy chain it to other parts, other electrical components. Okay, cool. So moving on, you go.
All right, so you guys heard Devesh mention a couple words fast there. You heard CAN and PWM. These two are basically the ways that we actually deliver signals from the RoboRio, which is the brains and the processor, out to the various devices that it controls. So there's sort of two, CAN and PWM are like the two possible ways to do that. Back in the day, PWM was like the only option and it's what we used exclusively. PWM is still the thing you're gonna see, unlike the VEX controllers. It has like a really iconic red, black, and white 3-wire cable that you guys have definitely all seen. PWM is the more basic of the two. It's a pretty simple concept here. What that stands for is pulse width modulation, which basically means that PWM sends a digital signal here, which you can see by that square waveform. And it has a period, which is a set amount of time that's consistent that the device that it's talking to is expecting to see, like it knows. So it knows, all right, like period, period, period. And what's doing is measuring how long its input is high during that period. So you can see on the graph here, that first line, the signal is high for 50% of it and then low for the rest of the period. You got 75%, the next one, 25%. The effect here is you're basically turning that device on and off really, really, really fast, like several thousand times a second. And the actual output you get is that 50%, 75%, 25% ends up being what the device will actually put out. So if you're giving this to a motor, for example, with PWM, you're basically turning it on full blast half the time and then off half the time. But you're doing it so fast that the actual output of the motor is about half the speed of the motor. Same thing with 75%, 25%. PWM is very simple. This is all it is. That has its upsides and that it's easy to program. It's very reliable. It's going to work no matter what. It has its downsides in that you can't really send much more data than you see in that little chart, which is how much to turn on or how frequently to turn on, I should say. And that means that it's also a one-way communication. So the RoboRio can send this signal out, but it doesn't actually know what the device on the other end is going to do. All the RoboRio knows is that it's putting out this % of the duty cycle. All right, and then CAN is completely different. CAN is actually more similar to like a USB, which is a universal serial bus. Serial bus basically just means that it's got one signal, just like the PWM, so a digital signal, but it can turns itself on and off very, very fast and essentially acts more like ones and zeros for like binary code. And through some very complex legwork by people who write firmware, CAN is actually a two-way communication system. So you basically connect everything in your robot with a single CAN circuit. That CAN circuit gets driven by I think it's the master in this, which is the RoboRio. That thing can send out messages and code basically to everything on the robot through one signal line. And through that same signal line, those devices can then talk back to the RoboRio. This is much harder. This is a more recent thing to come to FRC. This is the same technology that's in like cars and vehicles. This is what they use. It is much, much, much more powerful. It allows for some really advanced like speed controllers. And yeah, it's pretty good for that slide, Devesh. All right, so final call for us for PWM versus CAN. The ability for speed controllers to talk back to the RoboRio is extremely important for things like autonomous, especially. And it makes the wiring a little bit easier. So as opposed to having one PWM wire for every speed controller and every other device that needs PWM, you just have one CAN wire that runs its way around the robot. Upsides of PWM, much easier to program. It's going to work. And in like outside of FRC, there's a lot more cheap devices, things like Raspberry Pis and Arduinos and stuff like that. Pretty much everything can handle PWM. But for us, for our robots, CAN fits our needs a little bit better. It gives us more possibilities, and we have the software to be able to work with it.
Okay, so moving on to speed controller basics. So a speed controller basically, and I'm going to explain this more on the next slide, but a speed controller basically controls the speed of a motor, which it is linked to, and all speed controllers are linked directly into the power distribution board, which I covered. They receive a signal input, the PWM or the CAN, and they receive 12 volts from the PDB, which is directly because of the PDB taking all 12 volts from the battery directly. There's a conversion of signal input from the power output, and it delivers power effectively to the motor.
If I can jump in there 1 sec, Devesh.
Okay, cool.
The metaphor that I was taught with that to make that make sense is the signal input to the PWM or the CAN. You can imagine that as the thing that's opening or closing a gate to allow that water, the electricity, to go through. So the 12 volts is you're basically letting that run itself right up to the gate, and the signal, the thing that opens and closes the gate, is what allows that big 12 volt power to go through. So the PWM and CAN is very, very small amounts of power, very low voltage, whereas the 12 volts is like big, thick wires, meaning it's going to have a lot of current, and it takes a lot of energy to actually spin a motor. The speed controllers are a way to both separate your signal and your power lines, and to add the intelligence to decode the signal and get the gate in the speed controller to do cool things.
Yep. So yeah, for FRC, we actually, well, not for FRC, our team uses two speed controllers, the Talon SRX, the Victor SPX. And if you I guess look at any of our competition days, well, not competition days, but any of the days that we were working on the robot, all speed controllers are lined up right next to the PDB, and probably around like 14 are smushed side by side, 7 on one side of the PDB and 7 on the other. And they basically sprout off to all the motors needed on the robot. So moving on to the specifics, the Talon SRX is a high-end intelligent speed controller, and it has onboard controls that take off load from the Rio. So effectively, you can program it or monitor. So the Victor SPX is the second speed controller we use, and it has a less intelligent. It's basically less intelligent, where in the sense you can't actually monitor whatever or what is occurring with that speed control, but it can be set to follow the Talon SRX. Okay, moving on to FRC motors. So motors in general basically just provide power in the sense where they can be either turned on or off, and the power that they make is turned into rotational energy, basically, moving stuff such as rotating the wheels and etc. So motor selection is based on mechanical needs, and different motors are used in different scenarios depending on how much force you actually need to make something move. And generally there's a lot of motor types. For example, we use CIM, Mini CIM, 775, 775 Pro, Neo 550, and Falcon 500. And these are just all motor types. We don't use Neos yet, but it's something that hopefully we'll get to in the future, as they are smaller, and just better looking. But no, but they're hopefully what we're going to be going for. Yeah. So just a general overview of the things that we've covered. So all the green boxes on this chart, I guess, are things that we've covered, such as the Rio, the PDB, or the power distribution board, speed controllers, which, like I said before, are linked directly to the PDB, the switch, or the which is also connected to the battery, which isn't actually seen on here. And so these, I guess, are the bigger components that FRC uses. And in the following couple slides, we're going to be going over the other components, the smaller ones, such as the VRM, the PCM, etc. So get into it. So the first component I want to talk about is the PCM, or the pneumatic control module. And this basically controls and monitors all the airflow, or all the systems connected to airflow, or just dealing with the pneumatics. So on the left corner, I guess, you can see that the compressor, solenoids, the pressure switch are all connected directly into the pneumatic control module. And they, from there, are, I guess, controlled in that sense. So the PCM is connected to the Rio and the PDB via CAN wire, as Jason did mention. And it receives actually 12 volts directly from the PDB, but it only outputs 5 volts and 24 volts for pneumatic components, considering that we don't want to fry anything or just have it blow up. So that's something. So we're not going to go too deep into compressor solenoids and air tanks, but there are critical things we thought would be good to mention, as they deal with the air pressure, storing air, diverting air depending on what you need. And like I said, all of these things are plugged directly into the PCM.
You should say that pneumatics is enough of a topic to be its own workshop at a later date. For the sake of the electrical workshop, the PCM, the pneumatics control module, once that's wired up with its power and its CAN, pretty much everything else that does is part of software. And the other stuff we'd want to cover with pneumatics is largely mechanical, so it just doesn't really fit into this one. But if you guys are interested in that, we'll definitely make sure to get a workshop on pneumatics later.
Yep, yeah, that sounds right. Okay, moving on to the VRM. What I like to associate the VRM to is the PCM, while in the sense that it doesn't deal with pneumatic components, it does still distribute the 12 volts from the PDB to smaller components that may not be able to completely take those 12 volts. And it basically, it uses different ports to, I guess, split off the total power. So it's used to power low current devices, like I said before, the camera, the Raspberry Pi, and LEDs, things that just don't need the full 12 volts given by the battery. And in that sense, it basically just lessens the power. Okay, moving on to the radio and signal light. So the radio is on the top, the big white, I guess, block, and the light is the light. But what the radio does is basically it sends and receives data from the driver station, effectively giving a sense of Bluetooth, where you can see the Ethernet link, the Wi-Fi, and the power, and based on those four like, I guess, lights that are on the radio, you can tell what state the robot is in, if it's getting Wi-Fi, if it's getting power, blah, blah, blah. Moving on to the signal light. The signal light is pretty basic in the sense that it acts as a light where it can either be on and off, and it can also tell the state of the robot, whether it's enabled, disabled, in autonomous or teleop. And usually in an FRC match, these things have to be on. They're orange. So something to get into. So just a brief general overview. These are all the components that we have covered in this presentation so far. And I think this is the last, yeah, it's the last slide. Okay, so we covered a majority of these components. Of course, we didn't cover too much about limit switches and all the nitty gritty stuff associated to the VRM. But we did cover majority of it. And if you have any questions, you can set now.
Devesh, I just had a couple of clarifications on the speed controller slide.
Oh yeah, no problem.
So these two speed controllers, Devesh is right, they're almost identical, and the SPX is indeed a very, it's a less intelligent version of the SRX. If you look at the SRX on the top there, there's a small little port towards the right of it, and that's actually a data port which you can plug sensors into. And you can interact with those sensors in a extremely efficient way since it can run on the onboard computer on the actual SRX. And that's kind of the biggest merit that the SRX has over the SPXs, because you can run some kind of closed loop control system on the SRX itself and just have the SPX set to following mode. And then you have the same output that two different SRXs would give at the price of one SRX and one SPX. And the SPX also has some additional benefits, as it has the ability to be controlled via both CAN and PWM. So they're used for two different use cases. It's really up to the discretion of the team and the application.
Okay, sounds good. So I guess we're open for questions if anyone has any.
Are these slides going to be available for either download or to look at later somewhere?
Yeah, we can definitely
yeah.
throw these on Slack for sure. And this is
Yeah,
being
yes.
recorded just like all the other workshops. But yeah, I'll send out the file on Slack right now, actually.
Okay.
It's also worth noting that we are far from the first team to make an electrical walkthrough for FRC. That graphic that we're looking at right now is from Team 3161. WPI Lib, which is the like a big knowledge repository for software and some other parts of this, has great resources on like wiring, and it's a good way to like build your first robot, like put all this stuff together for the first time. If there's anything here you need more clarification on or whatever, Google will get you pretty much everything you need to know. This is a like FRC specific ecosystem, but all of these components individually exist out in the real world. And these are all like industry standard kind of terms. So you'll find tons and tons and tons of information on any of these things if you look them up.
Yep. Yeah, I totally agree. We didn't cover the different ways to actually implement these things, such as plugging in one thing to another, or soldering, or all of that stuff. But this is, like I said, this is a general presentation, so we hope we kind of helped everyone understand what the electrical system, I guess, is as a whole. So yeah, I guess we can end it now if no one has any questions. Jason, does that sound good?
Yeah, I think we pretty much covered little overview. Obviously, if anyone has more questions, we're always available, or, just, internet will get you most of these answers too. But whatever works for you guys.